Hello there, my name is Gethyn Jones. I've been a physics teacher for a number of years, 29 years in total, and I started my career in Wales many moons ago. Uh, but more latterly, I've been based in London, and I'm currently Director of Physics at Harris City Academy, Crystal Palace. A couple of other things. I'm a member of the Chartered College of Teaching, and I'm a council member, a teacher member on the council of the Chartered College of Teaching. And also, more recently, I contributed a chapter to the Research Ed Guide on Explicit and Direct Instruction. And that chapter was applying the ideas of Siegfried Engelmann and direct instruction to teaching electrolysis, and it was called Electrolyzing Engelmann. But today I want to talk about p-prims and the knowledge in pieces model. And okay, let's start with the knowledge in pieces model. So this has been suggested under various names, but the version I'm most familiar with is the version put forward by Andrea de Sessa, beginning in 1988. And talking in terms of physics, what de Sessa suggested was that intuitive physics, that is the physics that we are kind of automatically programmed with, our understanding of how the world works and how objects interact with each other, how we move heavy objects, how difficult it is to lift heavy objects. The pre-programmed physics that we all have. Intuitive physics is a fragmented collection of ideas, very loosely connected and reinforcing, having none of the commitment or systematicity that one attributes to theories. So de Sessa here is making what I think is a very valuable point, that people other than professional physicists don't necessarily have a coherent worldview on how the world works. Instead, we make sense of the world through interconnected, but not intimately interconnected ideas. And these ideas are not always systematic or coherent. As a good summary of his ideas, de Sessa quoted detective noir author Dashiell Hammett from his 1929 novella The Dane Curse. And this paragraph beautifully summarizes the situation in our students' minds, I think, but not only in their minds, but also in our minds. And this is the case much oftener, I think, than any of us would care to admit. And what Hammett said was, nobody thinks clearly, no matter what they pretend. Thinking's a dizzy business, a matter of catching as many of those foggy glimpses as you can and fitting them together the best you can. Okay, let's look at an example of this view of what knowledge is in action. If you ask a random selection of the world's population, which is larger, the Earth or the Sun, the correct scientific answer is, of course, the Sun. However, depending on the survey you read, roughly 10% of people will answer the Earth. Do they answer this way because they're stupid? I would say definitely not. Do they answer wrongly because their education, their formal education, has been neglected? Well, that's possible, but more likely, also argues de Sessa, is the fact that this is a question they simply haven't thought very much about. It's not on their radar, so to speak. So when somebody asks them what to their mind is a very strange, out of left field question, what they fall back on is what Decessa calls a p-prim. And what a p-prim is, it's a phenomenological primitive. And it's essentially a simple abstraction from very common experiences that are very basic or relatively primitive. And essentially, they require no explanation. They simply happen. So when you challenge someone about why they think that, for example, why do you think the Earth is larger than the Sun? Their response is likely to be a very puzzled, but it's obvious. It takes hours and days for us to travel around the Earth. But when you look up in the sky, the Sun is just a small looking disk. So it's obvious to my sense experience that the Earth is larger than the Sun. Or so they might argue. And I think this idea of a very basic way of seeing the world is a very important one. And I like Decessa's terminology, the p-prim technology. The p-prim terminology. Let's look at more about p-prims. So let's try looking at this example, which is one of my all-time favorites.
Okay, one last time. These are small, but the ones out there are far away. Small, far away. Forget it.
Okay, this is what I call the Father Dougal p-prim. And it's the idea that cow A and cow B are similar sizes because they look to be similar sizes. Now, I think this is a good example of a p-prim because it's a way of thinking about the world, a way of seeing the world, which is very, very basic. And although p-prims are not misconceptions, they can generate misconceptions when they are wrongly applied. A p-prim is like a semi-transparent filter. The world may look wrong when you look through this semi-transparent filter, but only when we choose the wrong p-prim to look out through. And for p-prims, context is absolutely everything. So what I'm suggesting is Father Dougal isn't necessarily stupid, but what Father Dougal is doing is he's looking out through the wrong p-prim. So the p-prim, that big objects look big, small objects look small. This serves us well in a remarkable variety of contexts. But when we're talking about looking at distant objects, it falls down. So that's an idea of a p-prim. It's a filter or a lens through which we look at the world and try and make sense of the world. Okay, so let's look at some examples of p-prims. Some of these have been suggested by Decessa and other authors. I've tended to make up some of the names myself. So the Father Dougal p-prim we've mentioned just now. It's the idea that the size of objects is directly relatable to how large they appear to your sight. Another one is, and this one is named by Decessa, is the Ohm's law p-prim. And again, this doesn't just apply to electrical circuits, as we'll look later. It's just the Ohm's law idea is just a nice label of it because we use it in many other contexts besides looking at electrical circuits. There's also the dynamic balance p-prim. This is named by Decessa, and another p-prim which I've taken to naming the Mathew Effect p-prim. So what I want to do is just look at a few examples of each of these p-prims and then go on to apply it to some ideas about science teaching. So let's move on and look at the Ohm's law p-prim. So what this says, and again I want to emphasize that we don't just use it to analyze electrical circuits, it's the idea that the more effort or input you put into a process or situation, then the larger the output. But on the other hand, the more resistance there is, the smaller the output. So applying it in a psychological context, you might be introducing a new way of working in, say, the science department. Now, if everyone lends a hand and everybody is enthusiastic about the idea, then it will be adopted very, very quickly and the output will be large, so to speak. On the other hand, if a number of members of staff oppose the initiative, then it's likely that the output is not going to be as large as you perhaps hoped. Now, I want to look at this also in an example of where it can be correctly applied and where it might possibly be misapplied. So let's look at a simple DC circuit. Now, if we apply the Ohm's law p-prim, and this isn't applying Ohm's law, it's just applying this idea that the larger the input, the larger the output. Well, if we adjust the output voltage of the DC power supply, then of course what would happen is we'd get more current and we'd also get more potential difference across the bulb. So the larger the input, whether you regard the input as the PD of the power supply or the current passing through the bulb, the larger the output is, as we'd expect. On the other hand, if we increase the value of the variable resistor, then what that will mean, of course, is that the smaller the output. So the current reading on the ammeter would be less if we increase the value of the resistor. And also, if we increase the value of the resistor, then the output, the PD across the bulb, would be less as well. So applying the Ohm's law p-prim, and I emphasize we're just naming a particular p-prim here, we're not implying that the Ohm's law V equals IR, although that's technically not Ohm's law, it's the definition of resistor, but lots of people call it Ohm's law, so we'll go with that. We're not directly applying Ohm's law, we're just looking at, say, an electrical circuit, and we're applying this very basic way of seeing the world, which we label the Ohm's law p-prim. Now, there's nothing wrong with applying the Ohm's law p-prim to this simple circuit, but we can indirectly apply it to a different circuit. So for example here, if I increase R2, increase the value of R2, you would expect, if you're applying the Ohm's law p-prim, the output voltage, which is across here, to decrease because you're increasing the resistance. So hence, if you're increasing the resistance, the smaller the output should be. But what actually happens, because it's a potential divider circuit, is the PD across the larger R2 actually increases, gets a bigger share of the PD of the power supply than R1 because it takes more energy for the charge to go through R2. So again, understanding how students view the world, if we're aware they're looking through the Ohm's law p-prim, then our explanation and the way we decide to teach this particular circuit may well alter. And what we're going to go on to do is look at possible ways in which we can cue which p-prim our students are going to be looking through when they view a particular situation. Okay, the next p-prim I want to look at is the dynamic balance p-prim. And the idea that here is that two opposing forces or influences, to make it more vague, can create a static equilibrium. Now, it doesn't just apply to scientific contexts. You might have the idea that, fire and ice oppose each other. So it can be applied in a psychological context as well. So possibly you might think of a very reactionary person and a very progressive person arguing about politics. And although there's a lot of heat generated by the argument, they kind of create a static equilibrium when nothing gets done, because the two opposing forces are kind of equal in magnitude in some way. And so this is a very basic way of looking at the world, which colors a lot of the way we look at different situations. But I want to focus on a scientific way, on a scientific example. So let's look at that. Okay, so if we're correctly applying the dynamic balance p-prim, it's very useful if we're talking about reversible reactions, for example. Buffer solutions springs to mind. So in other words, although the situation is not static, in the forward reaction possibly, molecules of the product are being produced. However, also molecules of the product are coming apart and forming their reactants again. But essentially what's happening is two dynamic influences, two dynamic processes are kind of working together and producing a static equilibrium. We think of this in many, many contexts, but it can be incorrectly applied. And one of the ways I've noticed that students incorrectly apply it is if we're talking about the motion of objects. So for example, if you tell them that, say, the drag force is, 100 kilonewtons and the thrust force is 100 kilonewtons, then again, that cues the dynamic balance p-prim. And they think, right, okay, two equally sized opposing forces must create a static equilibrium. Therefore, the plane must be stationary. In other words, because they're looking at the world through this basic lens, this p-prim lens of the dynamic balance, they think two opposing forces must create a static equilibrium. And they can't conceive, or they don't necessarily conceive possibly, that two opposing forces can create an equilibrium which is not static. So in other words, the plane can continue at a constant velocity, even, or not even, that's the wrong choice of word, but because of the fact that there's zero resultant force. Okay, now the next p-prim I want to look at is what I've termed the Mathew Effect p-prim. Now the Mathew Effect comes from Matthew 25:29, and essentially that can be stated as, to him that hath, more shall be given. So if we're correctly applying it, we can say that for example, it's a very useful p-prim if we're talking about the higher an object, what kind of energy is stored in the gravitational potential energy store, how much energy is stored in the gravitational potential energy store. And of course, the higher you lift it, the more gravitational potential energy is in the store. So it's a very helpful p-prim in that context. However, there's a different context where it's not so helpful. So if we're talking about gravitational potential, then that is not directly proportional to height or the distance from the center of the object with the gravitational field. It's actually inversely proportional. So if you're looking at things through the Mathew Effect p-prim, through the Mathew Effect p-prim filter, if you will, then your understanding of this is going to be, well, non-existent, basically, because your intuitive grasp of what's going on isn't the correct one to use in this particular context. And again, I'm returning to the idea that p-prims are not automatically misconceptions. Yes, they can generate misconceptions when they are wrongly applied, but what is really, really important, essential with all p-prims is the context into which you're applying the p-prim. And very often, p-prims can be applied perfectly correctly in a huge variety of contexts, and they're incredibly useful, and they form a basis for much of our cognitive activity. However, when they are wrongly applied, that's when they generate the misconceptions. And understanding how to trigger certain p-prims or how to cue certain p-prims can be really, really useful. Now, I don't think a lot of research has been done on this, but there's some interesting pointers as to how we can proceed from here. So let's look at some of those. Now, this is an approach I find really, really interesting, and it's an approach I've tried to build into my own teaching. And it's been suggested by Nelms in 2004. And what she argues is that we often use analogy to help students understand scientific concepts. And instead of trying to attack the misconception head on, possibly it might be more or as effective to cue the right idea using analogy. What is more, analogy on a very, very low key level. And Nelm suggests that this can be done possibly even without the pupils even realizing that you're actually cueing a certain p-prim. Educational jujitsu, so to speak. It's a really interesting idea. So let's look at an example that Nelms suggests. So she gets the idea of cueing correct ideas from the work of Dissessa, which we looked at earlier, and others on p-prims. And Nelms thinks of p-prims as small knowledge units. And in her view, they're cued to an active state to explain phenomena. So it's kind of like when you're asked to explain a certain thing, the p-prim kind of cuts in. You put the filter in front of your eyes to try and explain and predict what's going on. And what she's hoping to do with the techniques she's going to suggest is she's hoping that she can cue the correct p-prim by using an appropriate analogy, and possibly by using more than once on a very low key level, you can improve students' understanding without them realizing that they have been cued. So it's a really interesting idea. Now, one of the contexts NELMS looks at this is in the context of students' understanding of heat transfer, and particularly heat transfer by radiation. Now, the difficulty, in my view, comes from what has preceded this lesson, because very often this is part of a unit or a topic on heat transfer. So what students might have been taught previously is that good conductors are bad insulators, and equally good insulators are bad conductors of heat. So really, we're setting up a dynamic balance p-prim here without realizing that we're doing it. So if something is good at A, then it's not good at not A. So if it's good at conducting, it's not good at insulating. So we're setting a zero-sum game p-prim, or a dynamic balance p-prim here, in that something can't be good at A and also good at not A. So how can we get around this? Well, the problem is that we wish students to accept that, for example, a matte black surface is good at emitting infrared radiation. So it's the classic Leslie's cube experiment here, where you look at the infrared radiation from a white surface and from a matte black surface, and you say, okay, right, look, the matte black surface is much, much better at emitting radiation. Well, if the students have activated the p-prim we discussed earlier, the dynamic balance p-prim, what that means to them is that it seems natural to assume, well, if matte black is good at emitting infrared radiation, well, it can't be any good at absorbing infrared radiation. If it's good at A, it can't be good at not A. So this is the p-prim that they view. So there's a disconnect when we tell them, okay, let's look at the absorption properties of a matte black surface compared with a white surface. And of course, we do experiments, we do demonstrations to show students that, as a matter of fact, matte black surfaces are excellent absorbers of infrared radiation. So students are left with this uncomfortable disconnect between, well, that doesn't seem to make sense. And even if they have seen proper demonstrations, even if they've carried out the practical experiments themselves, possibly I think they might retreat to the p-prim because it's not necessarily something they spend a lot of time thinking about. And so if we're not thinking in terms of p-prims, we might not be really encouraging their learning at the deep level we all want to encourage students' learning to be at. So, if we want to cue the Mathew Effect p-prim, what can we do? Well, what we can do is we can possibly use very low level, low key analogies. And Nelms tried this, and she found some encouraging signs that this actually did help. So the low key analogy she suggested using with the students was things like, well, what do you have to be an effective communicator? Well, yes, you have to be good at taking in information, but you also have to be good at giving out information. So not only have you got to be a good talker, you've got to be a good listener. Something which defeats a lot of us in the teaching profession, I fear, including myself. So another low-key analogy you might care to use with students is the idea that effective netball players are good at throwing the ball, but they're also good at catching the ball. So they're good at A, but they're also good at not A. And this creates a different sort of p-prim, or activates possibly a different sort of p-prim to the dynamic balance p-prim, which was activated by the work they covered before on good insulators and bad insulators. So I think it's a really, really interesting way of thinking about this. So another context I'd like to look at, where I think the p-prim analysis can be really useful, is that suggested by David Hammer in 2000. And he was thinking about how students interpret situations such as a book interacting with a table. Well, what he suggested was students are perfectly happy to accept that a book can experience a force of gravity downwards, which, if unsupported, would tend to make it accelerate downwards. However, what he suspected was that many students, when you introduce a table into the picture, they don't think of the table as an active component of the situation. So they're thinking of the table as a passive object. So what they're thinking of is they're activating a blocking p-prim here. The book rests on the table, not because the table is pushing up on the book, but rather because the book is blocking the action of gravity. This is a very pervasive way of thinking, in my experience, for students, because they tend to think of some objects, especially inanimate objects like tables, as very passive components, and they can't see how it would generate a force necessarily. One way which Hammer suggested was a good way of stopping the blocking p-prim being activated is instead to show, or to start with, this situation where you have a spring on the table. Now, if you rest the book on top of the spring, then the spring gets squashed, and this activates what you might term the springiness p-prim. In other words, students are very happy to accept that this spring pushes upwards on the book, and therefore since the spring is pushing upward on the book, the table doesn't have any effect on gravity, so gravity is working on the book just as before, then in the situation without a table. So if we can activate the springiness p-prim, that means that students are much more likely to accept the situation which we want them to accept. In other words, that the book is at rest because the downward weight of the book is opposed by the normal reaction force produced by the table. And if you can activate the springiness p-prim before you go into the situation where you're talking about the book resting on the table, in my experience, students are much more likely to accept that and to internalize the scientifically accepted picture than if you don't. So it's just an approach which I think is highly effective. Right, the conclusion to this talk. So, firstly, I think awareness of the idea of p-prims, not necessarily by the name of p-prim, but just certain very basic ways in which not just students, but all of us look at the world and make sense of the world. These filters or lenses through which we look through, they color our view of what we're seeing to a remarkable extent. And if we're unaware of them, then that means that we're not seeing the world, or we may well be seeing the world wrongly. and not even realizing it because we haven't thought very much about it. And the knowledge in pieces model. Sometimes misconceptions research seems to think of every student as a closet Aristotelian. In other words, that they accept Aristotle's ideas. Aristotle's ideas are somehow built into the human brain. I disagree with that because, as De Sessa argues, I think a lot of our knowledge doesn't have the systematicity and the coherence that perhaps we would like it to have, or that subconsciously we feel that it has, when actually all of us have very messy internal minds. And I think this is consistent with the idea in modern cognitive theory of the idea that knowledge is organized in higher level structures which link different pieces of knowledge together as schemas. So I think awareness of this really, really, really helps your teaching and can help develop your teaching. I certainly feel it's benefited my own teaching quite significantly. This awareness and this idea that the students aren't necessarily lacking the IQ. It's just that they're looking at the situation wrongly. And if you can encourage them to view the situation in an alternative way through a different p-prim, if you like, then it really helps students' learning. At least that's what I've found in my experience. Okay, prior knowledge or ways of seeing, a p-prim is a nice way of summarizing this basic way of seeing, I think. They're not automatically unhelpful to learning, but they are highly context dependent. And if we can find a way of cueing the correct p-prim, of being aware of it, and maybe encouraging students to view certain types of situations through certain lenses or using certain basic ways of seeing the world, then I think it's going to be really, really good. Okay, so that's the substance of my talk over and done with. What I'm going to do now is I am going to just acknowledge the references. I was going to show a clip from Lord of the Rings, but I ended up not showing it, and I haven't altered the PowerPoint, so apologies for that. If you do want to look at that clip, though, it's really interesting, and it relates to the Father Dougal p-prim that we think of the size of the objects as being intimately related to the size of their appearance. In other words, big objects always look big, small objects always look small, or things that look small really are small, things that look large really are large. And I like thinking of that as the Father Dougal p-prim because of the clip. Okay, references. Hopefully I'll be able to embed links on the screen to this so you can access the references if you wish to. So these are the references I used. And finally, if you want more of my thoughts on education, I do write a blog. It's called E equals MC squared and that. Sorry, I'll say that again. E equals MC squared and all that. And the title is a nod towards a classic comic novel called 1066 and all that, which examined people's p-prims, if you like, about history. It's a very funny book, so I would recommend that you get hold of it if you can. And I write quite often on physics-related issues, and that's been interesting. I've been writing it for the past since 2013, I think, and it's been really interesting. And it's because it forces you to think when you're writing a post, you think very carefully about it. And oftentimes when I've started writing a post, I've reversed what I thought about it because I thought about it more carefully in the process of writing it. And a recent publication I had in the Chartered College of Teaching Impact magazine, which is just happens to be on a similar topic, perhaps a little more organized, of the talk that I gave today. Anyway, hope you found that interesting. Hope you enjoyed it, and hopefully in a few months we will be able to resume having Research Ed face to face. But thank you for viewing this video.